Thus far we've learned how to find derivatives of most of the basic functions, but not exponentials and logarithms. So the purpose of this video is to get at the derivatives of these two particular functions, types of functions. And to do that, we need some of the tools that we've built recently with chain rule and the inverse function theorem for derivatives of inverses. So let's start with the derivative of e to the x. Now, e is a special number. It's one of these transcendental numbers like pi. And we can approach finding its derivative using the limit definition. So it's been a while since we've used the limit definition. We've been using all these other rules to find derivatives. Let's go to that limit definition, because none of the rules that we've developed to this point give us the derivative of an exponential. So we would write it as the limit as h goes to 0, e to the x plus h minus e to the x over h. So we put the function in here at x plus h, the function at x, and then we're dividing by h. And remember, if you just plug in the limit, what you get is 0 over 0, right? So e to the x minus e to the x is 0, over h is 0. You get 0 over 0. So the question is, what does this limit really approach? All right. Well, we can factor out the x part here, and then what we're left with is e to the h minus 1 over h. So the real question is, what is this limit going to be? And so to find that, I've looked at, in a table here, taking values of h that are getting smaller and smaller and smaller, closer and closer to 0, and then evaluating this expression, e to the h minus 1 over h. And it starts out at 1.718. Then we go to 1.05. Now we're at 1.005, 1.0005, 1.00005. And what we see is that this is getting closer and closer to 1. And if you did this more and more and more, you would just see numbers that are increasingly closer to 1. The limit of this expression is 1. And that gives us a really interesting result. This derivative is just equal to the original function. So the exponential, e to the x, is its own derivative. It is the function that is its own derivative. The graph of the function, the graph of the derivative are the same. The slope of the function is equal to the function at every point. That's a very interesting result. So in a way, that kind of justifies the name that it's the natural exponential, because it's its own derivative. So let's take the same approach and try to find it for any arbitrary exponential. So instead of e to the x, where e is a specific number, let's take a to the x, where a could be any number. We could put any number in for a. Well, write the limit definition of the derivative. We use the same trick where we factor out the exponential, a to the x, so a to the x can come outside. And then the question is, what is this limit? And I'm not going to go through this here, but you could try, just like I did with e, making a table of different values, and every number you put in, you would get a different answer. So it's not always going to be equal to 1. It's only equal to 1 for that specific value of the base, being e, the number e. If this was the number 2, you would get a different result. If it was number 5, you'd get a different result. So we have sort of an answer here. This will be some number, but we don't know what the number is. And then we have the original exponential. So it's not quite as neat and tidy as e to the x, and we don't have a complete answer, but we're part of the way there. So to get all the way there, we'll need to take a pause and go in a different direction. Let's look at the derivative of the natural log. And I've written out here the derivative expression, d by dx of log, and then I've written it as y, where y we're assuming is e to the x. So I'm writing it as the composition of a function and its inverse. And we'll see why that is by the result that we get here. We can use the inverse theorem now to find the derivative of the log because we already know the derivative of e to the x. Okay, and then this will give us something that we can use to circle back to our original question. What's the derivative of a to the x, where a is any number? So y is equal to e to the x, and then we're taking d by dx of log y using the inverse theorem, or really what is the chain rule. We do d log y dy, so the derivative of log y with respect to y, the derivative of the natural log, and then multiply by dy dx, knowing that y is equal to this expression here. Because the log of e to the x is going to give you x, the derivative has to give you 1. This is just what we did with the inverse theorem. This is directly applying that here. Now what we find is, or what we can do now, is find that because y is equal to e to the x, its derivative is just e to the x, right? So dy by dx is just e to the x. And so we could find the derivative of this is just 1 over e to the x, but e to the x is just y, so the derivative here is just 1 over y. So now if we forget for a moment that we had set y equal to this, we've now just uncovered what is the derivative of the log of y being anything. No matter what y is, the derivative log y of log y is 1 over y. Or if you like, now you can switch the variables, like the trick that we use when we have inverses. You find the inverse and then you switch x and y. So the derivative of log x is just 1 over x. And here they are plotted. Here's the logarithm function. It's an increasing function, but its slope is decreasing over time. And that's why the 1 over x function works as its derivative. The slope is big here, and then it gets smaller. The derivative gets smaller as you increase the value of the function. So now what do we know? We know the derivative of e to the x is e to the x. The derivative of log x is 1 over x. Let's come back now to the arbitrary exponential, a to the x. And before I get to this part, let's look at the fact that log of a to the x can be written as x times the log of a. Okay, so this is just a rule of any logarithm. If you take the log of an exponential, you're allowed to bring down the exponent in front and multiply it. So log a to the x is x times log a. So we use this fact in this analysis. And now let's do what we were doing on the previous slide, which is taking the derivative of log y. But this time y is not e to the x, it's a to the x. It could be anything. So we're going to use this same trick, the inverse function theorem, but now that we know the derivative of natural log, the derivative we don't know is the derivative of a to the x, and we can use this expression to figure it out. Okay, so derivative of log y, where y is a to the x. We know what log y is. It's going to be x log a. So this result here is going to give us natural log of a. The derivative of this is just natural log of a. It's just a constant times x. Now inside here, we have derivative of log, natural log, which we know is 1 over y. And this is derivative of y, which is the unknown arbitrary exponential derivative. So this becomes 1 over y, and then dy dx is something we can solve for. It will be equal to y times log a, which is a to the x times log a, and that is our answer. The derivative of a to the x is a to the x times log a. And you'll notice this would also apply to the natural exponential, e to the x. So derivative of e to the x would be e to the x times log e. Log e is just 1, so that's why it's equal to itself. But for an arbitrary base, all you do is you take the function and you multiply by its natural log of the base. And that is the derivative of this exponential. So here, what do we have? We have y equals a to the x, and now let's think about an arbitrary logarithm. So if we match the logarithm to the base, you have the inverse operation, and you just get x. And so what's the derivative of this arbitrary logarithm? So just back up for a second. We found derivative of e to the x, derivative of natural log of x. Then we found derivative of a to the x. Now we want to kind of complete this story. What's the derivative of log a of x? Okay, but we use the trick, the inverse theorem. So we have log a y, and y is this exponential. So the inverse theorem gives us this times dy dx, and now it has to equal 1 because the log a of a to the x is just x. All right, so now we want to solve for this, and we know that dy dx is really just the derivative of this, which is a to the x times log a, or another way of saying that is y times log a. So what's the derivative of any arbitrary logarithm? It's 1 over y times log a. And again, change y back to x once you've got your inverse figured out. So the derivative with respect to x of log a x would be 1 over x times log a. All right, it's kind of a mouthful to say this all out, but this now gives us the derivatives of these specific types of functions, whether it's a natural log or an arbitrary logarithm, whether it's a base e exponential or a base a exponential, where a could be anything. We now have the formulas that we can use to find those. We don't have to go through this calculation every time. We can just use this formula to calculate the derivative of any logarithm. Now that we know how to take the derivative of a natural log, we can use that to take the derivative of expressions where you have a very complex exponential relationship by taking the natural log of the whole equation and then taking the derivative of that result. So this is called logarithmic differentiation. The process is outlined here on the screen. Let's see it in an example. It will give you a very complicated looking expression, but the process that we go through gives us the answer using the tools that we've developed, like derivative of natural logs, chain rule, and implicit differentiation. So let's go through that in an example. Okay, so here's the example. Y equals 2x to the fourth plus 1, that quantity to the power of tangent x. So it's an exponential, but it's not one that's simply where we can apply the rule for an arbitrary base exponential. The base is a function, the exponent is also a function, so we have a complex relationship here of a composite function. Now, to differentiate and find what is dy dx, first take the natural log of the whole equation. So by taking the natural log of the left-hand side, we just get natural log y. And on the right-hand side, because this is an exponential, we're allowed to bring the power down. So this becomes tan x times natural log of 2x to the fourth plus 1. So that's the first step in logarithmic differentiation, take the natural log. Then we can differentiate this equation. What is the derivative of this? Well, 1 over y times dy dx. So that's the derivative of the left-hand side. And in these types of cases, this is always what you get. You always get on the left 1 over y dy by dx. And then on the right-hand side, there can be a very messy looking expression like this. So what's the derivative of this thing? We have a product of tangent x and log 2x to the fourth plus 1, which is itself a composite function. So we have to use the product rule and the chain rule in the next step. So derivative of tangent is secant squared times the natural log 2x to the fourth plus 1. So the first step in the product rule is derivative of this times this. That's this part. Then the next step is this times the derivative of this, and for this natural log expression, we'll need to use the chain rule. We know the derivative of the natural log is 1 over its argument, so like 1 over y, times the derivative of the inside, dy dx. So 1 over 2x to the fourth plus 1, that's why there's a 2x to the fourth plus 1 in the denominator. And then what's the derivative of the inside? This is a power relationship here, 2x to the fourth, so bring down the 4, this becomes 8x to the third power, and then derivative of a constant is 0, so we just get 8x cubed. So this is the derivative of the right-hand side of that equation. Now to solve for the derivative of y, we just multiply by y, both sides. So on the left, we just have dy dx by itself, and then y is this expression, so I've just taken this expression here and multiplied this whole ugly mess thing. There may be a way to simplify this. It doesn't look obvious to me. It doesn't seem like a great use of time to think about this. So I could just leave it like this. This big ugly expression is your answer for dy dx. So the derivative of this thing is this whole mess, and we got there using logarithmic differentiation.